What's up, guys? Welcome back to this series on reinforcement learning. In this video, we're going to pick up where we left off with Markov Decision Processes and discuss the topics of policies and value functions. This will give us a way to measure how good it is for an agent to be in a given state or to select a given action. So let's get to it. In an earlier video, we discussed the general idea of MDPs and how an agent in an environment can perform actions and get rewarded for those actions. With all the possible actions that an agent may be able to take in all the possible states of an environment, though, there are a couple of things that we might be interested in understanding. First, we'd probably like to know how likely it is for an agent to take any given action from any given state. In other words, what's the probability that an agent will select a specific action from a specific state? We kind of touched on this when we discussed transition probabilities in an earlier video, but we'll expand on this idea by introducing the notion of policies in just a moment. Secondly, in addition to understanding the probability of selecting an action, we'd probably also like to know how good a given action or a given state is for the agent. In terms of rewards, selecting one action over another in a given state may increase or decrease the agent's return. So knowing this in advance will help our agent in deciding which actions to take in which states in order to maximize its expected return. This is where value functions become useful, and we'll also expand on this idea in just a bit. Let's first discuss policies. A policy is a function that maps a given state to probabilities of selecting each possible action from that state. We'll use the symbol pi to denote a policy. When speaking about policies, formally we say that an agent follows a policy. For example, if an agent follows policy pi at time t, then pi of a given s is the probability that the action at time t is equal to a if the state at time t is equal to s. This means that at time t under policy pi, the probability of taking action A in state s is pi of a given s. Note that for each state s in the state space, pi is a probability distribution over all the actions in the set of actions that can be selected from state s. Let's now move on to our second topic of interest, value functions. Value functions are functions of states or of state action pairs that estimate how good it is for an agent to be in a given state, or how good it is for the agent to perform a given action in a given state. This notion of how good a state or how good a state action pair is given in terms of expected return. Remember, the rewards an agent expects to receive depends on which actions the agent takes in which states. Since value functions are defined with respect to the expected return, this means that value functions are defined with respect to specific ways of acting. Since the way an agent acts is influenced by the policy it's following, then we can see that value functions are therefore defined with respect to policies. Now, we said that value functions are functions of states or of state action pairs. Well, we actually have two types of value functions: the state value function and the action value function. The state value function for policy pi, denoted as v sub pi, tells us how good any given state is for an agent following policy pi. In other words, it gives us the value of a state under pi. Formally, the value of state s under policy pi is the expected return from starting from state s at time t and then following policy pi thereafter. Similarly, the action value function for policy pi, denoted as q sub pi, tells us how good it is for the agent to take any given action from any given state while following policy pi. In other words, it gives us the value of an action under pi. Formally, the value of action A in state S under policy pi is the expected return from starting in state S at time t, then taking action A, and following policy pi thereafter. Conventionally, the action value function q sub pi is referred to as the q function, and the output from the function for any given state action pair is called a q value. The letter Q is used to represent the quality of taking a given action in a given state. we'll be working with Q functions quite a lot going forward. At this point in our reinforcement learning journey, we have an idea of the structure of MDPs, all the key components, and how within an MDP we can measure how good different states or different state action pairs are for an agent through the use of value functions. Be sure to spend some time on the corresponding blog for this video to ensure you've got the notation down and an understanding for the mathematical definitions of these functions. And also, don't forget to check out the DEEPLIZARD HIVEMIND for exclusive perks and rewards. Reinforcement learning algorithms estimate value functions as a way to determine best routes for the agent to take. In the next post, we'll continue this discussion by covering optimal value functions and optimal policies. Keep me posted on how your understanding of reinforcement learning is progressing so far in the comments. Thanks for contributing to Collective Intelligence, and I'll see you in the next one.
DeepMind also published this video. So they used reinforcement learning, and they built those skeletal models. Here, the neural network is predicting the power to send to the simulated muscles and joints of these models. And the reward is basically a positive reward whenever you manage to move forward, and a negative reward when you either move backward, or when you fall through a hole, or when you just crumple to the ground. The rest is just reinforcement learning, as we have shown you today. So all of these behaviors are emerging behaviors. Nobody taught those models.